Well, hey folks, welcome to this video. We're going to take a look at L'Hopital's rule. In fact, I'm going to break the L'Hopital's rule into two parts. So you can consider this to be part one. And L'Hopital's rule, it's a rule that comes about, it's really helpful in finding limits. Remember when finding limits, so you've been seeing in calculus, that the first thing you try to do when finding limits is substitution. And most of the time you did substitution, it gave you the indeterminate form 0 over 0. And when you saw the 0 over 0, in the past, maybe you went through some algebra manipulations. Maybe there was some factoring you did, or if trig was involved, you used trig identities. But there was always some sort of work you had to do. L'Hopital's rule is going to give us an alternative to finding limits that are in the indeterminate form, not only the indeterminate form 0 over 0, but also the indeterminate form infinity over infinity. Now notice how infinity over infinity, I'm parenthetically saying that really means infinity over infinity, or negative infinity over infinity, or infinity over negative infinity, or negative infinity over negative infinity. So rather than write down four different things, generically in math, we just kind of summarize them, all four of those, as being the case infinity over infinity. And, well, here it is. Here is L'Hopital's rule. F and g are two functions. And we're going to assume that these are two functions that are differentiable on an open interval I that's containing A. In L'Hopital's rule, we're going to have to assume that g prime of x does not equal 0 on this interval I. If the limit as x approaches A of f of x over g of x produces the indeterminate form 0 over 0 or infinity over infinity. So when you try substitution, it gives you one of those two indeterminate forms, 0 over 0 or infinity over infinity. Then the limit as x approaches A of f of x over g of x is equal to the limit as x approaches A f prime of x over g prime of x. That is L'Hopital's rule, or as I like to call it, the hospital rule. So when you have the indeterminate form 0 over 0 or infinity over infinity, boom, you can use L'Hopital's rule. And of course, the theorem ends with the little phrase, provided the limit on the right exists, or is infinite. Well, let's see. Now we've seen the rule, I suppose we should try an example. So let's evaluate the following limits. In part A, the limit as x approaches -1, x to the fourth, plus x cubed plus 2x plus 2, all over x plus 1. And then in part B, it's the limit as x goes to 0, sine squared 3x over x squared. So here's what you need to do. At this time, you need to pause the video. You need to write these examples down, pause the video. I'm going to head off to the chalkboard and work through these parts to this example. So make sure you have these examples, parts A and B, written down. Pause the video to do that, to write it down. And once you have them written down, restart the video, because I'm heading off to the chalkboard. Hey folks, this quick video, I'm going to call it L'Hopital's Rule Part 1. I'm going to break L'Hopital's rule into two separate videos, two separate parts. And the first part here, well, you should have written down, and I've just written down like the basic core, but in the previous slide you would have seen the theorem for L'Hopital's rule. And so I just kind of wrote down the core of the theorem, if you will, up here. Remember, when trying to do a limit, the first thing you try is substitution. If you get the form 0 over 0 or infinity over infinity, those are called indeterminate forms. We don't know what they are. We can't determine what they are. So far, what you've seen in calculus is that when you had one of those indeterminate forms, 0 over 0 in particular, there was some sort of algebra that you were able to do to eventually figure out the limit. Well, L'Hopital's rule tells us that when we have the form 0 over 0 or infinity over infinity, that this limit, as x goes to a, f of x over g of x, is equal to the limit as x goes to a, f prime of x over g prime of x. So you take the derivative of the numerator over the derivative of the denominator, and then try substituting. Hopefully you wrote down, I made a note that this infinity over infinity, it actually has, and I think I put it as a parenthetical comment on the prior slide, it comes in 4 different forms. It's either infinity over infinity, or infinity over negative infinity, or negative infinity over infinity, or finally negative infinity over negative infinity. We tend to look at all of those forms and just collapse it down and say infinity over infinity. All right, so that was the core of L'Hopital's rule, which I'll probably start calling the hospital rule from now on. It's where we take really sick limits. So it's the last thing you should have seen. You should have written this down. Was an example. It had 2 parts. Part A said evaluate the following limit. Limit as x goes to -1, x to the 4th plus x cubed plus 2x plus 2, and then all that junk over x plus 1. Notice if you substitute here, you know, what we've always done, what you've done and when you first started to do limits, you know, substitute -1 in for the x. If you toss -1 in for all the x's, this limit has the form 0 over 0. Now it's important that you verify that you're of one of these 2 forms, 0 over 0 or infinity over infinity. It's only when you're of the form 0 over 0 or infinity over infinity, it's only that form that you can take the problem off to the hospital. So since this is of the form 0 over 0, we can go to the hospital with it. And here's how I kind of denote that, you know, we are employing L'Hopital's rule. We're going to the hospital. Equal sign, I put a little L above the equal sign and circle it. That way, you know, when I look back at my work, I know from this step to this step I've employed L'Hopital's rule. So here we go, cranking it through L'Hopital's rule. So L'Hopital's rule says take the derivative of the numerator. So that's a 4x cubed plus a 3x squared plus 2 over the derivative of the denominator. Yep, that's just a 1. Now try substituting, and I think you'll see substitution works. Toss -1 in for the x's, and you should get, see, -4 plus 3, you should get a limit of 1. So that was the first example, but there was a part B. What I'm going to do now is I'm going to erase the board so I can get part B up here. This is going to take a little bit more work in part B. So here I go. If you need to, pause the video. Make sure you have this all written down because I'm going to erase the board. All right, folks, here we go. Part B. Notice that if you toss 0 in for the x, the form you have is 0 over 0. 0 over 0, so it's a candidate to go off to the hospital. So let's employ the hospital rule. So we take the derivative of the numerator. So you have to remember, let's see, chain rule up here. So let's see, the derivative of sine squared 3x is 2 sine 3x times cosine 3x times 3. And all that junks over 2x. So again, well, we had several applications of the chain rule in getting the derivative of the numerator. So folks, if you substitute here, if you substitute in, you're still going to get 0 over 0. So that means if we still have 0 over 0, just go back to the hospital one more time. See what happens. So we have to take this back to the hospital again. So here we go. Another trip to the hospital. So upstairs, but you know what? I want to simplify that. I just want to, it's not going to help a whole lot to simplify, but I do want to simplify a little bit. It just bothers me that I see a factor of 2 in the numerator and a factor of 2 in the denominator.
when I know I can cancel out those 2's. So I'm going to go ahead and just cancel out those 2's. And again, it's not like it's going to save me a lot of work, but hey, it just looks a lot better now. Since I did that, I am going to rewrite the numerator. Notice the numerator is a sine 3x times cosine 3x times 3. I think most of us are used to seeing the constant in front. So let me go ahead and get the 3 here. Not that it matters in the grand scheme of things, but that's just how my brain works. So here we go, we're cranking this through the hospital rule. It's of the form 0 over 0. So we get the derivative of the numerator. So now we have to remember the product rule here. So it's 3 times the product rule. So product rule, derivative of sine is cosine. So that's cosine 3x times 3 times cosine 3x. So it's the derivative of sine 3x times cosine plus sine 3x times, now the derivative of cosine is negative sine. That's negative sine 3x. Then my chain rule times 3. And all of that junk, that's not too bad, all that junk's over 1. So we can substitute now. If you wanted to, you could, clean that up a little bit. It's up to you. I mean, we are going to substitute, but if we wanted to clean it up a little bit before we substitute, this junk right here, that would give me a 3 cosine squared 3x, and then I'd have a minus 3 sine squared 3x. And now I toss 0 in for x, that's 0, cosine of 0 is 1, 1 squared, 1, 3 times 1 is 3, this is 0, so I get 3 times 3 minus 0, so I get the limit of 9. So part B, we just had to go to the hospital a couple of times, had to remember derivatives of trig functions, product rule, chain rule, a lot of good stuff. Okay, why don't we head back to the slides and let's see what we're going to do next with L'Hopital's rule.
All right, folks. Now that we worked through that example, let's see what I'd like you to do next. Oh, it looks like I'm going to want you to pause the video to do the following practice problems. So let's see what the practice problems are. Part A, find the limit as x goes to pi of 4 sine x over x plus cosine x minus pi plus 1. And part B, it's the limit as y goes to 2 y squared plus y minus 6 over the square root of 8 minus y squared minus y. So yeah, here's what I want you to do. I'd like you to do these 2 practice problems. Pause the video. Do these 2 practice problems. Once you've done them, restart the video, and I'll be at the chalkboard working through the solutions to both of these practice problems. So go ahead, pause the video, and do the problems, and then I'll see you at the chalkboard.
All right, hey, that last slide, I just basically said, it's your turn to practice a couple. So hopefully you did those. Hopefully you followed what I said. Told you to write them down. Told you to try them. See what you get as an answer. Restarted the video, and I said I would have worked out solutions. So here I am at the chalkboard trying to do a worked out solution. So the first one was the limit as x approaches pi, 4 sine x over x plus cosine x minus pi plus 1. The first thing I try, substitution. So I put pi in for the x. Sine of pi is, that's 0. So my numerator is 0. Denominator is pi plus cosine pi. Well, cosine pi is negative 1. So I have pi plus negative 1 minus pi plus 1. Now that would be 0 as well. So the form of my limit, the form is the indeterminate form 0 over 0. 0 over 0 is a candidate to head off to the hospital. So let's crank it through the hospital rule. And remember, it's the derivative of the numerator now. So 4 sine x, the derivative is 4 cosine x, over the derivative of the denominator. The derivative of x is 1. Derivative of cosine is negative sine. Derivative of pi is 0. Derivative of 1 is 0. So that's it. Now we try substituting. And when we substitute, let's see, we'd have a 4 times cosine of pi, that's negative 1, over 1 minus sine of pi, that's 0. So it looks like we get negative 4 to be the limit. So I hope you got negative 4 as the limit. Going to have to erase this to do part B, so bear with me while I erase the board, and then I'll do part B. Okay, part B, I asked you to find the limit as y approaches 2 of y squared plus y minus 6. All of that junk over the square root of 8 minus y squared minus y. So we toss 2 in for the y's. That should be the first thing you do, is toss 2 in for the y's to see what form you have. We get the form 0 over 0. So it's a candidate. Let's crank it off to the hospital. So here we go. Derivative of the numerator is a 2y plus 1. Derivative of the denominator, now remember this is 8 minus y squared, that quantity, to the 1/2 power. So again, remember that this remember it's that. So here I go, finding the derivative, and I get 1/2 8 minus y squared to the negative 1/2 times the chain rule, so it's a negative 2. And then derivative of y is 1. Well, we have a little bit of, hopefully a little bit of cleaning up to do here. Limit as y goes to 2. Not much to do in the numerator. Let's leave the numerator as 2y plus 1. I mean, not much else we could do there. In the denominator, I have a 1/2 times a negative 2 right here. 1/2 times negative 2. So that'd be a negative 1. And I'm going to get rid of this negative exponent. So I'm going to take this first block of junk here, and I'm going to rewrite that as negative y over. So to make this exponent positive, I would drop it into the denominator, and that would make it a positive 1/2 exponent. So that's 8 minus y squared to the 1/2. And don't forget the minus 1. Going to try to substitute here. Hopefully substitution will give me something friendly. So 2 goes in for the y. 2 times 2 is 4. 4 plus 1 is 5. All right, feeling pretty good. The numerator's a 5. Downstairs, I'd have a negative 2 over. Let's see, 2 comes in here for y. 2 squared is 4. 8 minus 4 is 4. 4 to the 1/2 power. Square root of 4 is 2. Well, it looks like substitution's working here. So 5 over, see, negative 2 over 2, that's a negative 1 minus 1. We better get the limit of negative 5/2. Okay, so hopefully you got both of those practice problems. I call it like the basics of using the hospital rule. So hopefully you got both of them, and it's making sense. Why don't we head on back to the slides, and let's see what's awaiting us in our voyage here on the hospital rule.
All right. Hopefully you got those 2 practice problems correct. And as we've seen, we saw in the very first example, sometimes one application of the hospital rule isn't enough. We saw in part B of the first example that I did that we had to take it back to the hospital a second time. I wanted to do one more example that illustrates this process, that you might have to do L'Hopital's rule or apply L'Hopital's rule more than one time. So in this example, we're going to evaluate the limit as x goes to pi, or I'm sorry, limit as x goes to infinity of 4x cubed minus 2x squared plus 6, and all that junk over pi x cubed plus 4. So pause the video if you need to, but write this example down because at this time, I'm going to head off to the chalkboard to work through this example.
All right, the last slide, we talked about you might have to apply, L'Hopital's rule more than once. We've already seen that in an example, but I thought I'd do another example. So here's one more example of, you might have to apply L'Hopital's rule more than one time. I think I was also really looking, wanting to look at an example where we had the indeterminate form infinity over infinity. Notice if you think about substituting here, you really can't because infinity is not a number, it's a concept. But if you think about it, you're putting extremely large values in for x. The form you're going to have here is infinity over infinity. That is a candidate to go off to the hospital, infinity over infinity. So here we go, cranking it through the hospital rule. So we have the limit as x approaches infinity, derivative of the numerator to 12x squared minus 4x, derivative of the denominator 3 pi x squared. All right, folks, if you think about substituting, you still have the form infinity over infinity. Got to go to the hospital again. So, one more trip back to the hospital. Gives us the limit as x goes to infinity. Derivative of the numerator, 24x minus 4. Derivative of the denominator, 6 pi x. All right, sweet. Hey, let's substitute or think about substituting. We still have the form infinity over infinity. Back to the hospital. So here we're going to the hospital 3 times. So here we are heading off to the hospital a 3rd time. And let's see here, the derivative of the numerator is 24. Derivative of the denominator is 6 pi. Nothing but constants, and we know the limit of a constant is that constant, so we get the limit, we finally get the limit to be 24 over 6 pi. Actually, it looks a little nicer to simplify it down to 4 over pi. So that example had to go off to the hospital a total of 3 times. So let's head on back to hopefully finish off this introductory or part 1 of L'Hopital's rule. So we got to head back to the slides to see what other kind of indeterminate forms we could encounter. So let's head back to the slides.
All right, we saw we had to do the hospital rule 3 times to get that limit of 4 over pi. And we're going to conclude this introductory or this part 1 video by pointing out, there are other indeterminate forms out there. So far we've just been dealing with the indeterminate forms 0 over 0 and infinity over infinity. 0 times infinity or infinity minus infinity, those are 2 other indeterminate forms. They're kind of like the off-brand indeterminate forms, but they're still indeterminate. We don't know what 0 times infinity is. We don't know what infinity minus infinity is. So they are indeterminate forms. So if we have a situation with one of those off-brand indeterminate forms, in order to use the hospital rule, you can only use L'Hopital's rule when you're in the form 0 over 0 or infinity over infinity. So if it's 0 times infinity, can't use the hospital rule. Infinity minus infinity, can't use the hospital rule. Only when you have the form 0 over 0 or infinity over infinity. But as we'll see in the next example, what do we do when we have these forms 0 times infinity or infinity minus infinity? So in this example, part A, we're going to find the limit as x goes to infinity of 3 over x times cosecant 5 over x. Notice here, that as x gets really large, as it approaches infinity, 3 over x gets close to 0. 5 over x gets close to 0. But the cosecant of 5 over x, well, that would be getting close to, well, infinity. The graph would have a vertical asymptote. So the form here is 0 times infinity. So it's going to be an issue we have to address. Part B, we're going to do the limit as x goes to infinity of x minus square root x squared plus 4x. Notice this is the form infinity minus infinity. So what you need to do is, if you have to, pause the video to write down these two examples. Once you have it written down, I'm going to be heading off to the chalkboard to work through this example.
All right, as we saw in the previous slide, there are other indeterminate forms. 0 times infinity, don't know what that is, that's an indeterminate form. Infinity minus infinity, we don't know what that is, that's an indeterminate form as well. When we encounter those indeterminate forms in doing limits, we cannot apply L'Hopital's rule. Remember, L'Hopital's rule only applies when you have the form 0 over 0 or infinity over infinity. So if we encounter one of these off-brand indeterminate forms, the 0 times infinity or infinity minus infinity, our first task is to manipulate things around to get it into the 0 over 0 or infinity over infinity form. We have to get it into a form where we can take it off to the hospital. And I think this example here is going to show us exactly what we're talking about. Part A, let's find the limit as x heads off to infinity of 3 over x times cosecant 5 over x. Now notice in this form, as x is getting really large, 3 over x, well, as x gets really large, 3 over x gets close to 0. 5 over x gets close to 0. So the form is 0 times, well, if this is getting close to 0, remember cosecant, remember there's a vertical asymptote at x equals 0 for the graph of cosecant. So that means the form is 0 times infinity. Cannot take this to the hospital. It's not sick enough yet. We have to get into the right form to go to the hospital. So here's an idea. We know there's a relationship between cosecant and sine. Specifically, cosecant is the reciprocal of sine. So maybe that's where we start off here. Maybe we start off with looking at the cosecant of 5 over x and saying, well, you know what? That's 1 over the sine of 5 over x. But just kind of rewriting the whole thing as 3 over x over sine 5 over x. Cosecant 5 over x is 1 over the sine 5 over x. Multiply those together, we get this. So we have to start off doing a little bit of trig. But notice the form that we're in after we did that little bit of trig. As x goes to infinity, our numerator is 0. So the form, it's kind of like a progress check on the form we're in. The numerator is 0. 5 over x is 0. As x gets really large, 5 over x gets really close to 0. Sine of 0 is 0. We now have it in the indeterminate form 0 over 0, so that means we now have it in the proper form that we can go off to the hospital with it. So let's take this off to the hospital. And let's see, derivative of the numerator. Well, I look at the numerator, 3 over x. I visualize that as being 3x to the negative 1. So the derivative is negative 3x to the negative 2. Derivative is negative 3 over x squared. Denominator. Well, we know the derivative of sine is cosine. So we have cosine 5 over x. Now the chain rule, we have to do the derivative of 5 over x. I visualize 5 over x as being 5x to the negative 1. So the derivative is negative 5x to the negative 2. Or negative 5 over x squared. Now we can simplify here. In fact, that's my next step, is just actually going through the simplification. This negative 3 over x squared over negative 5 over x squared. Okay, now that mess right there, first we know a negative divided by a negative is going to become a positive. But the 3 over x squared divided by 5 over x squared, that's just going to simply reduce to 3/5. So we'd have a 3/5 times, and then we still have the 1 over cosine 5 over x. And now as x gets really large, x heading to infinity, the limit as x goes to infinity of 3/5 is 3/5. Remember, the limit of a constant is that constant. So I'm talking about an old limit property. There was an old limit property that said a limit of a product is equal to the product of the limits. So I'm saying the limit as x goes to infinity of 3/5 is 3/5 times the limit as x goes to infinity of 1 over cosine 5x. Well, as x gets really large, 5 over x gets close to 0. Cosine of 0 is 1. So the limit as x goes to infinity of 1 over cosine 5x, that's 1 over 1, which is 1. Simplifies down to 3/5. All right, so here's what you need to take note of here. Start off, you were of the form 0 times infinity. You need to do a little triage on it, a little prep work. The prep work, you had to get it into a form where it was then appropriate to go to the hospital. So here it was recognizing cosecant 5 over x is the same thing as 1 over sine 5 over x. So that little bit of trig, got it in the right form. Then we were off to the hospital, simplified, evaluated, and we were done. But there was one more part to this example, part B. So let me erase the board, and let's see what's happening with part B. All right, hey folks, here in part B, we're asked to find the limit as x heads off to infinity of the quantity x minus square root x squared plus 4x. Notice the form it's in right now. It's in the form infinity minus infinity. Infinity minus infinity, that means we need to do some work. We need to do some prep work. We can't go to the hospital right now. It's not in the form to go to the hospital. So this gets a little creative. So a little creative algebra. But look at what's under the radical. X squared plus 4x. I'm going to go under the radical and I'm going to factor out an x squared. So if I factor an x squared out of x squared, well, I have a 1. If I factor x squared out of 4x, I'm left with 4 over x. Okay, that hasn't changed the form. Whoops, let me get another parenthesis here. You know, we still have the form infinity minus infinity, but notice what we can do now. I can now rewrite this as x minus x square root 1 plus 4 over x. Okay, I know what you're thinking. Hey, Bill used that property, the square root of a times b. You can rewrite it as the square root of a times square root of b. But square root of x squared, I thought square root of x squared was absolute value of x. Well, square root of x squared is absolute value of x. But we're talking about x heading off to infinity, so we're talking about x being positive values. So if x is positive values, absolute value of x would just simplify to x. All right. Looks like we're getting somewhere. We haven't changed the form though. We still have the form infinity minus infinity. But look what we can do now. You have x minus x times the square root. Out of this mess here, you can factor out an x. So let me try to get one more line here where we factor out the x. So we have x times a 1 minus square root 1 plus 4 over x. Okay, now notice by doing this one little step of factoring, while we have been in the form infinity minus infinity, infinity minus infinity, infinity minus infinity, we're now in a different form. We're in the form infinity times, and this would be 0, because that, 4 over x, as x goes to infinity, 4 over x is getting close to 0. This is square root of 1, square root of 1 is 1, 1 minus 1 is 0. So this one little step of factoring has changed us from infinity minus infinity to infinity times 0. Still not a form where we can go to the hospital, but at least we've changed the form. So let me pull the problem up here. And let me just say, in pulling it up here, I'm going to employ one more bit of algebra magic, if you will. This is multiplication. X times this junk. I can rewrite this as a division problem. I can take this mess and I can rewrite it as 1 minus the square root 1 plus 4 over x divided by 1 over x. Remember that when you're dividing, division is the same thing as multiplying by the reciprocal. So if you saw this ugliness, 1 minus square root 1 plus 4 over x divided by 1 over x, you could say, well, you're going to rewrite this division as this mess multiplied by the reciprocal of the denominator. Well, the reciprocal of the denominator is x, and that would give you this mess here. So I guess I'm implying an old algebra trick. It's not a trick, it's just a fact, that multiplication and division can be rewritten. Anytime you see division, you can rewrite it as multiplying by the reciprocal. I just took the multiplying and rewrote it as a division statement. And look what form that gives us now. That one little algebra trick, if you will, has now put me in the form of as x goes to infinity, of 0 over 0. Once I'm in the form 0 over 0, I can now go to the hospital. So we better take this beastie off to the hospital now. And let's look at what we get. Well, up here, the derivative of 1 is 0, so we're at a negative 1/2, 1 plus a 4 over x to the negative 1/2 power. Yeah, mentally I rewrote 1 plus, a square root of 1 plus 4 over x is 1 plus 4 over x to the 1/2 power. So it's that times chain rule. I'm going to do the derivative of 1 plus 4x. That's negative 4 over x squared. All over the derivative of the denominator is negative 1 over x squared. And boy, if I clean up here, let's see, we got a lot of craziness going on. First off, I know negative 4 over x squared divided by negative 1 over x squared. I know that's going to simplify to just a positive 4. So positive 4 times negative 1/2. Positive 4 times negative 1/2, that's a negative 2. And I'm not going to do any more algebra simplifying because I'm kind of running out of room. As x heads off to infinity, 4 over x, it's getting close to 0. 1 plus 0 is 1. 1 to the negative 1/2 power is 1. Negative 2 times 1, negative 2. So I know there's a lot going on in this one, but the big picture, infinity minus infinity, can't go to the hospital. So we had to do some prep work. We did quite a bit of prep work in order to get it to a form, here it was 0 over 0, where we could go to the hospital. So what's embedded in here, yeah, there were some algebra tricks, but I'm sure you're going to be happy to have seen those algebra tricks. So that's it for part 1 of L'Hopital's rule. Thanks for watching.